Everyone, and welcome to the Simons Institute Breakthroughs lecture today on thresholds. So just a brief introduction. So my name is Venkat Guruswamy. I'm a senior scientist here at the Simons Institute. And the Simons Institute is the leading worldwide venue for collaborative research in theoretical computer science. It was established in 2012 with a generous grant from the Simons Foundation. And ever since then, it has been hosting programs in a variety of areas in theoretical computer science and its interface with sciences, engineering, humanities, economics, and so on. And in addition to the thematic programs, two of which run every semester, the Institute also does a lot of outreach activities in bringing exciting developments in theoretical computer science to a worldwide audience. And so it's in that capacity. Today's breakthrough. So today we have one such series is the Breakthroughs lecture series, which brings exciting scientific and computational breakthroughs to a wide audience. And so before I introduce today's speaker, I will just a quick update on how to ask questions. So this is a hybrid event. I mean, we have a lot of people here in the room asking questions here. Just raise your hand, easy. I'll also be monitoring the Zoom chat. So if there are any questions there, you can raise your hand and just unmute yourself and ask, or type it in chat and I'll relay the question to the speaker. Okay, so with that, let me introduce today's speakers. Our distinguished speaker today is Jin-Young Park from Stanford University, where she's a Sego assistant professor working in combinatorics. And previously, Park was a member of the Institute for Advanced Study in Princeton from 2020 to 2021. And she received her PhD from Rutgers University in 2020 under the supervision of Jeff Kahn. Her doctoral work earned the 2022 dissertation prize from the Association for Women in Mathematics. And before she started graduate studies, she worked as a mathematics teacher in secondary schools in Seoul from 2005 to 2011. So, and today she will lecture, today's talk is about thresholds. I think it'll be hard to get a shorter title than that, but it conveys a lot. And with that, please join me in welcoming Jin-Young.
Thank you very much for this invitation. It's my great pleasure to give a talk in this amazing place. So I'm going to talk about thresholds today. And so here is my plan for today. So in this talk, I will introduce the Kahn-Kalai conjecture, which is a central conjecture in probabilistic combinatorics, and then discuss our results related to it. But we first start with a brief introduction to random graphs, just to begin with a concrete picture in mind. And also historically, random graph theory was the starting point of our story. But later we'll see that the setting of our work is much more general. So let me first talk about random graphs just briefly. And here we use GMP for the random graph. So GMP is the Erdős-Rényi random graph, whose definition is this. So the vertex set of GMP is the bracket n, which means the set of integers from 1 up to n. And here we think n is finite, but it's very large. So it's like 1,000 or thousands, millions, billions. It's a large fixed number, a finite number. And so because we have n vertices, so there are n choose 2 potential edges, and we choose each edge independently with probability p. So for example, so this is a little example of GMP when n is 3 and p is 1/2. So in this case, we have 3 vertices. So we have 8 graphs in our sample space. And because p is 1/2, so every graph in our sample space has the same probability, which is 1/8. But as we change the value of p, the probability distribution also changes. So for example, if p is very small, like 0.0001, in that case, the sparse graphs are much more likely. On the other hand, when p is close to 1, then the denser graphs are much more likely. So GMP is not a fixed graph, but this is a probability distribution. So it makes sense to ask questions such as, what's the probability that GMP is planar? Or what's the probability that GMP is connected, etc. And in those questions, we are not exactly interested in finding the precise probability for those events, but whether we are interested in what's the typical behavior of GMP for given probability p, or as we change the values of p. And so for that, in this talk, we are going to use the term with high probability. And when we say GMP does A with high probability, that means the probability that GMP does A tends to 1 as n tends to the infinity. So in our work, usually the interesting range of usually P is a function of n, and usually P tends to 0 as n tends to the infinity. So usually like P is like 1 over n or log n over n. So a function in n that tends to 0 as n tends to the infinity. That's our interesting range. And one striking thing about GMP is appearance and disappearance of certain properties are abrupt, and this gives us the notion of thresholds. So one way to view the behavior of GMP is this evolution model, which means we think of GMP as we add edges 1 by 1 at random. So for example, when P is 0, when we are here, then there are no edges. So this is our starting point. But at the end, when P is 1, we see all of the potential edges, which is n choose 2. And as we slowly increase P from 0 to 1, we view this as we throw random edges 1 by 1 each time. So that's the evolution model of GMP. And in this model, so one typical example is this. So when we think about the typical maximum size of connected components of GMP, so here I say typical because, as I said, GMP is a probability distribution. So we are interested in the typical behavior of GMP. And when we look at the maximum size of connected components of GMP, then if n times P is slightly smaller than 1, in this case, the maximum size of connected components is very small. So it's at most in the order of log n. So this is very small compared to the number of vertices in GMP. On the other hand, when n times P is slightly larger than 1, then suddenly we see a giant component whose order is as large as n. So in this sense, we can say that P equals 1 over n is more or less the threshold for having a giant component. So this is where the phase transition happens when we look at the maximum size of the connected component. And this is just one example, and we see this like interesting phase transition for many other interesting properties. So it became a natural interest. Naturally, it became a central interest in probabilistic combinatorics to find thresholds for various properties. Okay, so here I put some of the past results on finding thresholds, and I'm not going to read all of the results in this list, but I just wanted to show my audience that this is indeed a long-studied area, and many researchers have worked on the problems in this area. But also, when you look at the list, you'll see that study on this area has been done mostly for specific properties. So for example, what's the threshold for GMP to have a small subgraph? For example, having a triangle or having a fixed size clique, or what's the threshold for GMP to have a perfect matching? So those are some specific properties, but later we'll see that the Kancalai conjecture suggests a unified bound for the location of thresholds, which includes most of these results listed on this list. So that's where we are heading to. But for that, I think I need to introduce the notion of thresholds first. So, okay, but do we have any questions so far? Right.
Pedantic question. You mentioned connectivity and spanning trees, two different things. How,
Oh, did I say that?
The last one.
Oh, so this spanning tree, this means the given type of spanning tree. Yeah, okay. Do we have any other questions? Okay. Then let me talk about, let me introduce thresholds. So basically, this slide contains all of the basic definitions that we are going to talk about today. So as I said, the setting of the Kancalai conjecture is much more general. This is something beyond the random graph theory. So here we use X for a finite set, and this X can be anything. So we are not necessarily stick to the random graph setting. So X is a finite set, and 2 to the X is, as usual, the power set of X. So this is the collection of all of the subsets of X. And we use mu p for the p-biased product probability measure on 2 to the X, which means for any subset A of X, mu p of A is defined to be p to the size of A times 1 minus p to the size of the complement of A. And then we use XP for the random variable whose distribution is mu P. So this is, simply speaking, this is just a P random subset of X, which means we choose each element of X with probability P independently. So this is the meaning of a P random subset of X. And then maybe it looks familiar to us. So for example, if we take X to be n choose 2, which means the set of all of the edges in Kn, where Kn is the complete graph on n vertices. So if we take our ground set this way, then XP is just GMP, which is the Erdős-Rényi random graph, because we choose each pair or each edge with probability P independently. Or we can also view this as the edge percolation on the complete graph Kn. So under this definition, the random graph model is just one example of this model. And another model that we can think about is if we set X to be the collection of all of the K clauses from n variables, then we can view XP as a random CNF formula. So here X really can be any finite set, and we can think about this random model on any given finite set. Then let me introduce the notion of an increasing property. And basically, this is a generalization of the many properties that we consider. And simply speaking, an increasing property means we can't destroy this property by adding an element. There's a simple description of this property. But formally speaking, we say F is an increasing property if whenever B contains an element in F, then B is also contained in F. So for example, in the random graph example, the property that the given graph is connected. This is an increasing property because we can't destroy this property by adding an edge. And also another example is to contain a triangle, because again, we can't destroy this property by adding an edge. And another example is, so if we think about random CNF formula, then another example for an increasing property is to be not satisfiable. So in my mind, an increasing property looks like the picture on the right-hand side. So this big circle or small circle is 2 to the x with the natural process structure. So we have the empty set at the bottom, and we have the entire set on the top. And for example, in the first layer, we have all of the singletons. And in the second layer, we have all of the doubletons, etc., with the natural process structure. So for example, whenever we have an element A in this increasing property, then everything that contains this element A is also contained in the increasing property. Okay, so those are the basic definitions. And do we have any questions so far? Yes?
All the properties you listed previously, increasing properties?
I think so. Yeah, I can't go back, but yeah. Yes, that's true. So everything is increasing property. Okay. And can we move on? Because I want to lose my audience from this definition page. Okay. Now let me introduce thresholds. A well-known fact is that for any increasing property F, as long as this is not the empty set or the entire set, mu P of F, which is by definition the probability that our random variable XP satisfies the given increasing property F, this is continuous and strictly increasing in P. So this continuity is very easy to see. This is just from the definition. So when you look at the definition of mu P of A, this is just a polynomial. So mu P of F is just a sum of so many polynomials. So this is again polynomial. So obviously this is continuous. And this strictly increasing property, strictly increasingness is, this is a baby example of a coupling argument, but let me not go into the details. But by this fact, we know that if we draw the graph of mu P of F, then this graph looks like this. So as we increase P from 0 to 1, mu P of F also increases from 0 to 1. And one simple example is the connectivity. So for example, if you think about the connectivity, then if P is 0, then of course the probability that GMP is connected is 0 because it's just a bunch of isolated vertices. So the probability, so in this case, mu P of F is precisely 0. On the other hand, when P is 1, then the probability that GMP is connected is exactly 1 because all of the edges are present. So we are here. And we know that as we increase P from 0 to 1, the probability that GMP is connected or XP satisfies the given increasing property also increases from 0 to 1. So we have this increasing graph. And then because this graph is continuous and strictly increasing, so of course, so there exists something called PC of f, for which UP of f is exactly 1/2. And this PC of f is called the threshold for f. So roughly speaking, the threshold is where the phase transition happens, because this graph says that if we are below the threshold, then it's less likely or it's unlikely that our random variable xp satisfies the given increasing property f. On the other hand, if we are above the threshold, then it's much more likely that xp satisfies f, the given increasing property f. So this is where the phase transition happens, and this is definition of the threshold. But if you're familiar with the random graph theory, then you have seen the definition of an Erdős-Renyi threshold, which is defined this way. So it says, so the threshold in this sense, the threshold is if p is much smaller than p0, then UP of fn is, it tends to 0 as n tends to the infinity. So here we consider a sequence of increasing property, a sequence of ground set, a sequence of the increasing properties. And if p is much larger than p0, then this probability tends to 1 as n tends to the infinity. So this is a classical definition of an Erdős-Renyi threshold function. But by a work of Bolobash and Thomason, we know that our definition of PC is always an Erdős-Renyi threshold. And moreover, if we apply our definition, then we don't have to consider a sequence of events or sequence of increasing properties. So in some sense, our notion of the threshold is much more convenient to work with. Okay, so this is the definition of threshold. And do you have any questions about this basic notion? Okay. So there are roughly two interesting directions of the study of thresholds. The first direction is about location of thresholds, which is the main theme of today's talk. And as I said, historically, most of the interesting work was on thresholds for specific properties. And then the Kancke-Lai conjecture suggests a general bound. So what happens, so as a preview, what happens is this. So given an increasing property f, we are curious about the location of its threshold. We want to find it. But usually this is very hard to find. But in many cases, there is something called Q of f. We're going to define it later, but for now, let me just call this Q of f. There is something called Q of f, which always gives a lower bound on the threshold. And then the Kancke-Lai conjecture says that this PC of f is also bounded above by this easy lower bound Q of f times some tiny error term. So if this conjecture is true, then the location of the threshold is trapped in this tiny window. So that's a rough statement of the Kancke-Lai conjecture. And so, yeah, so the most recent result is the proof of the Kancke-Lai conjecture. And another direction of the study of thresholds is called the sharpness of thresholds. And there are, again, many interesting work in this direction. And all of those work is based on Fourier analysis. So after they got those results, as far as I know, people tried to use Fourier analysis to prove the Kancke-Lai conjecture. But again, as far as I know, it didn't go well. And so it turned out our proof of the Kancke-Lai conjecture has nothing to do with Fourier analysis. It's very much like combinatorial. Okay, so yeah, so let me move on to the next part, the Kancke-Lai conjecture. And in this part, I'm gonna give my audience what motivates the Kancke-Lai conjecture. And so the authors of this is a very strong conjecture, and even the authors of this conjecture said it would probably be more sensible to conjecture that it is not true. And so in this part, I'm gonna introduce 4 examples, and through those examples, what I want to do is to give a feeling to see why this conjecture is believed to be nonsense, or why people believe that it should be untrue. Anyway, so the question behind, the fundamental question behind this conjecture is this: what drives the threshold? And we're going to examine 4 examples to build up some observations to answer this question. And in the first example, our x is n choose 2, so our random variable xp is gmt, and the given increasing property is to contain a copy of h, where h is this tiny graph. And the question is, what's the threshold for GMT to contain a copy of H? And so here in this question, we are interested in the number of copies of H in GMP. So this is a numerical random variable. And whenever we have a numerical random variable, the first thing that we want to check is its expectation. So we start from its expectation. So if we compute the expected number of copies of H's in GMP, then this is up to, so this means up to a constant vector. We're going to ignore constant vectors in the rest of the talk. So this expectation is equal to n to the 4 times p to the 5, where this n to the 4 is the number of potential copies of H's, because H has 4 vertices, so we have roughly n choose 4 many H's. And then this p to the 5 is the probability for each H, because H has 5 edges. So the probability for each H to exist is precisely p to the 5. So this expectation is n to the 4 times p to the 5, and we know that this tends to 0 if p is much smaller than this value. And this tends to the infinity if p is much larger than n to the negative 4/5. So in this sense, we can say that the threshold for the expectation is equal to n to the negative 4/5 up to a constant vector, because this n to the negative 4/5 is where the phase transition happens in terms of the expectation. Well, so if you're familiar with the random graph theory, we know that, So first of all, we know that this n to the negative 4/5 is a trivial lower bound on the threshold, because if the expectation goes to 0, then x is 0 with high probability. So by the definition of the threshold, if the threshold must be at least as large as n to the negative 4/5. So this gives a trivial lower bound, but we know that it is well-known fact that the threshold for this increasing property is actually equal to n to the negative 4/5. This is easy using the second moment method. So from this example, we see that there is a close relationship between the expectation calculation and the actual threshold. So at this point, maybe we can dream that the expectation predicts the correct threshold. And if this is true, then it would be uninteresting. Yes?
Precisely define your symbol, the approximation symbol?
Which symbol?
Well, you're using it a few times, right? Well,
you mean this
approximation symbol?
Or this one?
Well, I guess, both of those, I guess.
So the second one means same order, which means we ignore constant vectors. And the first one has the same meaning. So we just ignore all of the constant vectors. We just focus on the order.
Is this constant?
Yeah, no constant. Yeah. Okay. And then, so this means much smaller. So the ratio tends to 0. Okay, yes?
Basic question. I guess this argument applies to any subgraph.
Sorry?
This threshold applies to any calculation of such a finite subgraph, right?
So we have the second slide. Please be patient. Okay. So we have the second question, our second example, which will answer your question. So in the first example, it's like a freshman's dream. So we observed this one example, and then we dreamed that, the expectation calculation always predicts the right threshold, but that's not true. So in the second example, we consider another small example, another small graph, which is K. So now K is this. And then the question is the same. What's the threshold for GMP to contain a copy of K? And again, we start from the expectation calculation. And so the expectation is n to the 5 times p to the 6. So if p is much smaller than this, then the expectation tends to 0. And then we do the same calculation to see that the threshold for the expectation is n to the negative 5/6 of the constant vector. And again, this gives a trivial lower bound, because as I said, if expectation goes to 0, then there's no copy of K with high probability. So we can ask the question, is the threshold equal to this trivial lower bound? But in this case, the answer is no. The truth is the threshold is equal to n to the negative 4/5. Then why do we have this difference? But there is a reason for this discrepancy. So here, actually n to the negative 4/5, this is the threshold PC. If you still remember the previous example, this is PC of FH, right? So this means the threshold is not determined by the expectation of K, but the expectation of H. And in general, this is true. This was proved by Erdős-Renyi and Bolobash. So roughly speaking, for any fixed graph K, the threshold for containing a copy of K is equal up to a constant vector to the threshold for the expectation of the densest subgraph of K. So in this case, when you look at K, the densest part of this graph is H. And in other words, as soon as we contain a copy of H, then this tail it doesn't matter. The tail just follows in this density of the edges. So yes, so this result by Erudesh, Renyi, and Bolobash tells us that whenever we are considering a fixed graph, then basically we know everything about the threshold because the expectation calculation just gives us the right threshold. So we are done with a fixed graph. And then what's the natural next step? Because we are done with a fixed graph, so the next step is to consider a growing graph. So in the next example, we consider a perfect matching, where perfect matching means this. So we have disjoint union of edges that covers all of the vertices. This is perfect matching. And our question is the same. What's the threshold for GMP to contain a perfect matching? Of course, we have the assumption that 2 divides n, because otherwise this problem doesn't make sense. Okay, so again, we start from the expectation calculation, and this gives us 1 over n. So the threshold for the expectation is 1 over n. And then, so trivially, the threshold is at least 1 over n. And the question is the actual threshold equal to 1 over n? But in this case, the answer is no. The threshold is log n over n. And in the previous example, we saw that as long as we consider the densest subgraph of the given graph, then its expectation gives us the right threshold. But when you look at the perfect matching, there is really no densest part. It's just whenever subgraph you choose, we see the same density. So there's really no densest part. And so that means there is really this non-trivial gap between the actual threshold and the expectation threshold. Okay, so we have this non-trivial gap. Then what do we do next? We want to understand why we have this gap. And that's the next slide. So this is where we are. We know that as long as we consider a perfect matching, the threshold for the expectation is 1 over n, while the actual threshold is log n over n. But actually, this log n over n is another trivial lower bound on the threshold. This is because of the fact that if p is much smaller than log n over n, then GMP has an isolated vertex with high probability. And because now we are considering a spanning graph, so as long as there is an isolated vertex, then of course there's no perfect matching. So this gives us another obstacle from having a copy of a spanning graph. And let me elaborate this problem just a little bit more. So this fact is due to the coupon collector problem. So the situation is this. I guess everybody is familiar with this elementary problem, but let me explain this. So this problem says this: each box of cereal contains a random coupon, and there are n different types of coupons. And the question is, how many boxes of cereal do we typically need to buy to collect all of the n coupons? And here I put typically because, again, so if you are terribly unlucky, then it will take forever to collect all of the coupons. But we are looking at the typical behavior. And here, another important assumption is the coupons are uniformly distributed, and which is not exactly close to the reality. So in reality, usually there is some coupons that are impossible to collect. Anyway, so in this ideal situation, the answer to this question is n times log n. So we need to buy n times log n many cereal to collect all of the different coupons. And then how does this coupon collector problem relate to our isolated vertices? So in our setting, we have n vertices, and those are our coupons. And as I said, random graph model can be viewed as we throw random edges one by one. So in that model, throwing edges can be seen as we buy cereals, 2 at a time. So, and then this coupon collector problem says that if the number of edges is much smaller than n times log n, then typically we have an uncollected coupon, which is an isolated vertex. And then the number of edges corresponds to the value of p much smaller than log n over n, because there are roughly n squared many potential edges out there. So this tells us that if p is much smaller than log n over n, then typically there is no perfect match or no spanning graph. Okay, so we just saw that. So there are, so this is the third example, and let me consider one last example. And in this example, we change our ground set. Now X is n choose R, which means we have n vertices, and then we collect all of the R tuples out of those n vertices. And then in this model, XP is a random R uniform hypergraph, HRNP, which means we choose each R tuple with probability P independently. And then in this model, we ask, or people ask the same question. So when R is larger than 3, what's the threshold for HRNP to contain a perfect matching? And of course, here we assume that R divides N. And here a perfect matching means a collection of disjoint R tuples that cover all of the vertices. Okay, so this is called Shamir's. So this problem was suggested by Elie Shamir. So this is called Shamir's problem, and this question was very hard. But okay, so for example, when R is 2, then somehow this problem was very easy, and this was already proved by Erudich and Renyi in 1966. But somehow when R is larger than 3, then this problem gets much, much harder. And basically this is because when R is larger than 3, then we don't have an analog of Hall's theorem or Tuss theorem, or we have very weak analog of those theorems. So that makes this problem much harder than R equals 2 case. Anyway, so this problem was notoriously open for about 30 years. But we can think about some like easy lower bounds as we observed before. So for those calculations, let me fix R equals 3. And if we start from the expectation calculation, then we see that we can compute that the threshold for the expectation is equal to n to the negative 2 up to a constant factor. So this gives the first lower bound. On the other hand, if we consider the coupon collector behavior of collecting vertices, the coupon collector behavior of the isolated vertices, then from there we have a second lower bound, which is log n over n squared. So here, again, we see this log n gap between the first lower bound and the second lower bound. And it was proved by Johansen, Kahn, and Wu in 2008 that the actual threshold is log n over n squared. And this was a very hard result, and they received the Fulkerson Prize out of this work. And it took about 30 years to prove this conjecture. And here again, we see this log n gap again. So it's time to summarize all of our observations. So the fundamental question behind the Kancke-Lie conjecture was what drives the threshold? And from the previous examples, we saw some trivial lower bounds on the location of thresholds. So from the first two examples, we saw that the threshold for the expectation gives a lower bound on the location of the threshold. And from the last two examples, we saw that the coupon collector-ish behavior pushes up the first lower bound by log n. So there are some easy ways to get lower bounds. And historically, in many, many interesting cases, the main task is to find a matching upper bound. And so in this situation, the Kancke-Lie conjecture roughly says that for any increasing property, the threshold is at most log x times the expectation threshold. And so as I said, this is a very strong conjecture. For example, this immediately implies historically very hard questions. For example, the example that we just saw. So threshold for perfect hypergraph matchings, which is proved by Johansen, Kahn, and Wu. So this is how the conjecture works. So we can easily compute that for any given R, the expectation threshold for having a perfect matching is n to the negative R minus 1. So if we apply the Kancke-Lie conjecture, then we have this upper bound. But this upper bound matches the second lower bound, which is gotten from the coupon collector behavior. So this hard question, the Kancke-Lie conjecture, if the Kancke-Lie conjecture is true, which we know now is true, then this immediately implies this hard question is just one-line computation. And so another hard question is the threshold for bounded degree spanning trees. And this is called the tree conjecture. And this is recently proved by Montgomery a few years ago. And again, in this question, we have an easy lower bound, and the Kancke-Lie conjecture gives an upper bound that matches the trivial lower bound, the second lower bound. So those are some hard problems that are implied by the Kancke-Lie conjecture. And if you compare the years of those problems, then this Kancke-Lie conjecture comes before those work. So this means at the time the Kancke-Lie conjecture came out, those problems were still widely open. And actually, as far as I know, those questions were the motivation for the Kankhalai conjecture. So people wanted to solve those problems, but those problems were so hard. And if you have some hard problems and if you don't know what to do with them, then what do you do? One thing that we can try to do is to make those problems even harder. So they just conjectured, maybe we can just say that for any increasing property, the threshold is at most the easy lower bound times log n, which immediately implies those hard questions. Okay, I see many hands. Okay, so yeah.
I was going to say, it looks like you've converted the problem into one of getting a better lower bound.
I converted the problem of getting lower bound, getting better lower bound.
I mean, if one proves the Kankhalai conjecture, one's still left with, in general, one is left with the issue of proving a better lower bound.
Oh, okay. So later we'll say that there are some easy ways to get a lower bound.
Lower bound, which is log n better than the expectation.
Oh, aha. Okay. No, I don't think there are better lower bound because those lower bound matches. So this coupon collector lower bound matches the upper bound.
No, that's in some examples, but in general, you still have this log n gap between the upper and lower.
Yeah, sometimes we have log n gap and sometimes we don't have.
That was a comment.
Oh, I see. Okay. Okay. Yeah. Yes.
Related question: the examples that you gave shows that for those examples, actually the upper bound, the one which is expectation factor log, is the right answer. Is there some general understanding for what problems that is the right answer for? That?
Yeah. So that is one of the open problems that I'm gonna pose at the end. So yeah. So
is there a formal statement for this open problem? Because the way I ask this is kind of open-ended. There's a formal.
No, so we are still in the stage to find the patterns. So there are questions with like not just log n gap, but some a gap with which is something much smaller than log n. And we are still trying to find the pattern. What decides the gap between the lower bound and the true threshold?
So for containing that graph with the tail, it seemed like the true threshold was like more than a log times away from the expectation threshold, right?
More than log.
Yeah, I mean, you had to correct it by just considering the like densest subgraph, but how would you correct that expectation threshold in general if it's not, like the.
It's common.
Okay.
Yeah. Okay. So in those examples, what I introduced was not the true definition for the expectation threshold, and the true definition is common.
Because that's the code C.
Yeah.
Okay.
Yeah. So this is still a rough statement.
Sorry, if you're already talking, can you clarify what the densest part was? Because the graph contained a triangle and it was not a click, so I was kind of confused.
Oh, so in that context, there are many different densities, but in that context, density means a graph that gives the highest expectation threshold. In other words, it's the number of edges divided by number of vertices. Any other questions? Okay, let me continue to. Okay, so now, so it's here. So what's the expectation threshold? As I said, in the previous examples, it was pretty obvious to see whose expectation we want to compute. But as I said, in our setting is much more abstract. And if the given increasing property is just any abstract thing, then it is unclear whose expectation we want to compute. So we need a careful definition for the threshold for the expectation. And so this is the definition page. Okay, so we start from an observation. And in this observation, we give a lower bound on the threshold. And the observation is this. So we say that we know that Q is a lower bound on the threshold if there exists some hypergraph G, some collection of sets G inside 2 to the X that satisfies the following two properties. The first property is called G covers F. This means whenever we have an element, for every element in F, we have an element in G such that A contains B. So whenever we have an element A in F, we have another element in G. So this is definition of a cover. And
is bigger than D, so A, that looks like F is above G.
So I think when we talk, for example, when we talk about like vertex cover or edge cover, so what's a vertex cover? That means we want to cover all of these edges, all of those edges with vertices. So in that sense, vertex is smaller than edges.
Also, it covers every A in F. Right? The quantification is universal over A in F. So for everything in F, something happens. So,
but I understand your question. This is not covered. It's covered. Okay. So another visualization of this picture is this. So this is my 2 to the x, my favorite 2 to the x picture, and an increasing property looks like this, and then a cover looks like this. So this means if we collect everything above each element in this cover, then this contains F. So I say, so this, I use this symbol. So I introduce this symbol only for the proof part, but I'm not sure if we have time to go over the proof part. Okay, so then, let's just stick to this picture. Okay, so this is the picture of cover. So this says, if we consider the offset generated by G, which means we collect every element above each element in G. So the offset generated by G contains the increasing property F. So this means this is what it means by G covers F. And the second property is this. If we consider this quantity, then this is not large, this is small. And actually what's in the left-hand side is precisely the expected number of S's in G, S's in XQ. So here, what is Q to the S? This is the probability that S is contained in XQ. And then we just add them up. So this is precisely the expected number of S's that are contained in the random subset XQ. And then we say, so we give the restriction that this expectation is not large. And as long as we have the expectation small, then this Q gives a lower bound on the threshold. So the justification of this observation is straightforward, but let me not go into the details. You can do it. I mean, this is very straightforward. Sorry? Oh, so X sub Q is just another way to say X sub P. So X sub P was the P random subset, which means we choose each element with probability P, and XQ is we choose each element with probability Q independently. Okay, so again, the justification for this observation is very straightforward, and let me not go into that one, but instead, let me connect this observation to one of our past examples. So in the second example, we consider the increasing property to contain a copy of K. So in my 2 to the X picture, the increasing property looks like this, right? So this circle is the collection of all of the graphs, and then F consists of all of each graph that contains at least one copy of K, okay? And in this picture, there is an obvious choice for a cover. We can just take G1 to be all of the labeled copies of Ks, which means G is just this. Then you see that obviously G covers F because the offset generated by G contains the increasing property F. And in this case, then we have to check the calculation in number 2, excuse me. So the expectation, the calculation in number 2 is just the expectation calculation for the copy of Ks. So in this case, this expectation calculation, we did this before. This calculation gives that Q is at most n to the negative 5/6, our first lower bound. So it tells us this n to the negative 5/6 is the first lower bound on the threshold. But in that example, we saw that we can do better. We have a better cover. So this time we can choose G2 to be all of the labeled copies of H's, where H is the densest part of K. And if you choose if you choose G2 this way, then the expectation calculation gives us that Q is at most n to the negative 4 pips. And then, so we have this better lower bound on the threshold. So the lesson from this observation is whenever we have a cover, then this cover gives us a lower bound on the threshold. And different cover can give us different lower bounds. So the natural definition for the expectation threshold is we just choose the maximum on all of the lower bounds. So yeah, and again, this is a trivial lower bound on the threshold because we chose the maximum among all of the lower bounds. So this is again a lower bound. And then the formal statement of the Kancke-Lie conjecture is this. So it says that there exists a universal constant K. So K comes first. K does not depend on anything. And K is a reasonable constant. So from our proof, K is about 1,000, but we haven't tried to optimize K. So I believe it can be much smaller. But I don't think it can be 1 or 2, but it can be like 100. I think we can achieve that. Anyway, so there exists a universal constant K such that for every finite set X and increasing property F, the threshold is at most K times the expectation threshold times log of the size of the universe. So this is the formal statement of the Kancke-Like conjecture. And in the next part, I'm going to introduce our results, and if time allows, then maybe some of the proof. Yeah.
So there's some way to relax the notion of a cover to something like the approximate cover or something.
Yes, it's coming.
That's what's going to happen.
Yeah, okay, it's coming. So yes, so that's the first, yes?
What would we get with triangles as covers?
I'm sorry?
If we had triangles, it would be a weaker lower, it would be a weaker lower.
So if our increasing property is to contain a couple of triangle, is that your question?
Construct a cover by using the triangles.
You mean in this example? Oh yeah, sure. In this example, if you use a triangle, then it will give us lower bound 1 over n, which is smaller, yes.
In this example, do we know G2 is optimal? Do we know that's optimal?
You mean, is this the optimal lower bound?
Yeah.
Of course.
For expectation.
Of course, yes, because it matches the upper bound.
Yeah, but is there a direct way of proving that?
Okay, so this is the definition for the expectation threshold, and the expectation threshold is not always the best lower bound because of the log and gap. So sometimes the coupon collector gives the better lower bound. But in this, we know that for a fixed graph, then this G2 or something like G2 is always the best lower bound because it matches the upper bound.
Maybe ask this, it looks at people need to calculate the lower bound.
Okay.
So many G's you might have to try.
Yeah, that's true. But maybe there is some other things coming, so maybe we can take a look at the slide
this kind of tensor subgraph can be found in polynomial lines. So it's maximum.
So, but there are some other things, so maybe we can go. So yeah, so far it looks very hard to compute the optimal cover, but there are some other things coming. So the first result in this direction is a conjecture of Talleyrand, which is called the fractional version of the Kancke-Like conjecture. So in this version, we define the fractional expectation threshold for F. I don't want to give the precise definition for this, but roughly speaking, this just means we replace the cover G by a fractional cover, which means, so a cover G can be regarded as a 0,1 function defined on 2 to the x, but we just replace this 0,1 function by a real valued function. And then we apply something similar to the definition of a cover. So we consider a fractional cover, and then that gives a lower bound on the threshold, and then we choose the maximum among all of the lower bounds. And from this definition, of course, the fractional expectation threshold is an upper bound and the expectation threshold, because a cover is just a special case of a fractional cover, and because we always choose the maximum. So a fractional expectation threshold is always an upper bound on the threshold, but this is still a lower bound on the threshold. And then what we proved a couple of years ago is this result. So this was a conjecture of Talleyrand, and this was proved by Frankston, Narayanan, and myself. So basically, we proved the Kancke-Like conjecture, but with PE replaced by PE star, the fractional expectation threshold. And then what was better was we replaced log of the size of the universe by L of F, where L of F is the size of a largest minimal element of F, which means, so for example, okay, so let's say this is F, then L of F means we consider all of the minimal elements of F, and then we choose the maximum size. This is L of F. So in particular, if we consider the containment of a fixed graph, in that case, L of F is always a constant. So that means in this inequality, there is no gap between the threshold and the fraction, between the threshold and the fraction expectation threshold. They're equal up to a constant vector. So this is weaker than the Kancke-like conjecture. Here I said weaker because of this fact, because the fraction expectation threshold is an upper bound on the expectation threshold. So this does not address this improvement. Anyway, but what was important, what was interesting about this result was in all of the known applications, the expectation threshold is equal to the fraction expectation threshold up to a constant vector. So this means all of the result followed from the Kancke-like conjecture is also implied by the fractional version of the Kancke-like conjecture. So our result in the past already gives all of the applications of the Kancke-like conjecture. And what's better, I think, in application-wise, this was useful because when we consider the fraction expectation threshold, then using the LP duality, there is a way to give an upper bound on the fraction expectation threshold. And the way we apply this conjecture or this result is to compute that upper bound given by the LP duality, and that gives us an upper bound on the fraction expectation threshold, and so that gives us an upper bound on the actual threshold. And that upper bound matches the trivial lower bound. So that's how we can nail down the actual threshold. And the proof of this conjecture was inspired by Always, Lobet, Wu, and Zhang, their breakthrough in Erdős-Rado sunflower conjecture. And and the proof of this conjecture was pretty short. So our paper itself is not very short because we have to contain all of many of the interesting applications of this result, but the actual proof part was about 4 pages. So it was not very long. And so this was one of the results. And after we got this result, of course, the natural next question was, what's the gap between the expectation threshold and the fraction expectation threshold? So as I said, in all of the known applications, the expectation threshold and the fraction expectation threshold, they have the same, they are equal up to a constant vector. And indeed, it was conjectured by Talleyrand that for every increasing property, the 2 parameters are equal up to a constant vector. And of course, this conjecture implies the equivalence of the Kancke-like conjecture and the fractional version of the Kancke-like conjecture. And before we proved the Kancke-like conjecture recently, proving this conjecture was regarded as the most likely way to prove the Kancke-like conjecture. And we made some partial progress. So for this conjecture is very hard. Even simple instances of this conjecture are not easy to establish. And Talleyrand himself suggested 2 test cases, which is proved by DeMarco and Kahn and Frankston-Kahn and myself separately. But even for these test cases, we needed some non-trivial proof argument. Yes.
Why is the P star worse than P?
Is it just worse than?
Worse in the sense like, why not just state the whole conjecture in P star and be done with it?
Because I don't know. Because considering a cover is more natural. We are doing discrete math and then considering.
So is it harder to compute if you consider the fractional version compared to the discrete version or something?
Oh, no, it's not like that. So, and also so the origin of this conjecture is from the graph containment. And then in that version, we just think about the containment of subgraphs. So we just actually in some version of this conjecture, people just define the expectation threshold to be a fixed subgraph, like computation for the fixed subgraph. We don't consider all of the custom covers. So in that sense, considering this expectation threshold is much more natural, I think.
So one question for the hypergraph matching, for example, do you get anything from the fractional version?
Oh yeah. So as I said, the fractional version gives an You mean a lower bound or an upper bound? So fractional version always gives a lower bound.
Right, but you already proved in the previous result that the fractional version of the upper bound, right? In terms of the max. So if you apply just that theorem to the hypergraph matching, do you get the resolution of hypergraph matching? Or
yes. Yes, as I said.
From the fractional part.
Yes, everything that's implied by the integer version is also implied by the fractional version. So basically, so I don't know if this is a good way to say, but the integer version, so we proved the integer version of the Kancke-like conjecture, but so far we didn't find any additional application of that.
Okay.
So yeah, I think I shouldn't say this. but that's just application-wise. But theoretically, I think giving a bound using the cover is much more like elegant than giving a fractional cover. And I hope that we can find some theoretical application for that. Anyway, okay. So
just to check, the conjecture is still Talleyrand's conjecture.
Yeah, so I can say that, so we are still working on this conjecture, and I can say that at least we know something more than what's written here, but still the general conjecture is widely open. Okay, so this is this is the approach before we prove the Kancke-like conjecture, and then also one remark is now that we prove the Kancke-like conjecture, we know that the fraction expectation threshold is at most k times the expectation threshold times log of L of f, which means if L of f is a constant, then we know that there's no gap between the fraction expectation threshold and the actual and the expectation threshold. It's just so hard to say. Anyway, so this is the current status. And then most recently, we proved the Kancke-like conjecture. This is proved by myself and Hui-Pham. So yeah, we proved this conjecture and we still keep this L of f. So this means if L of f is small, then there's no gap between the expectation threshold and the actual threshold, which matches the result of Bolovash and Erdős-Renyi. Anyway, so our proof is inspired by, again, the previous work, sunflower result and fractional Kancke-like work, but the implementation is different. So I think, how much time do I have?
It depends. We have time till 5, but you could stop anytime and we can do the rest as sort of
okay.
Or we can go on. Okay.
Looks
like the audience is interested, so.
So yeah, so what I have in the next part is to prove, well, maybe I can skip this or I can leave this for the discussion session or like after this talk and then move on to open questions. Is okay?
Just no, show some of
okay. I don't know how the timeline was. So I was told that I'm gonna have like 30 minutes of discussion session after this talk. Is that true?
Yeah, so maybe what you can do is, yeah, you can do the open questions and still, if people want to leave, they have to leave, they can leave, and then I guess whoever stays, we can go.
Okay, is that okay?
You're supposed to.
Okay, let me skip it. For now, let me skip the proof part and then go on to open questions. So, okay, so this is where we are. We know that PC is at most is at least PE and at most PE times log L, but still, so the Kancke-like conjecture gives an upper bound. So still there is a gap between the actual threshold and an upper bound. And so the natural question is what characterizes the gap between the expectation threshold and the actual threshold? So proving the Kancke-like conjecture is not the end of the story, but this is just the beginning of the story. And in many cases, this log L gap is tight, and we have some examples, but there are some cases for which log L gap is not tight, and we view them as good test cases. So we are still working on trying to understand the size of the gap, what characterizes the size of the gap. And so the first successful test case is this, something called the square of a Hamilton cycle. Well, because I don't have so much time, so let me not talk about what it is. But anyway, this is a spanning graph, and the expectation threshold is n to the -1/2. But the conjectured upper bound or the conjectured true threshold is also n to the -1/2. So even if this is a spanning graph, but there's no gap. And here you see, this is the history of improving the upper bound. And I hope people see how much effort we have to put to improve just one log and on upper bound. And finally, we proved that, we proved this true upper bound. And for this one, I think what's interesting is we used the argument in the fractional Kancke-like. So in all of those work, up to here, all of this work used something called absorption method, which is pretty involved, but our argument is pretty simple, and our entire paper is about like 5 to 6 pages. So the argument is pretty short. Oh, by the way, our recent resolution of the Kancke-like conjecture is also short. Our entire paper is 6 pages, and the very last page is only for the references. So our actual paper is not very long. But again, that paper is short because we didn't put any applications of that. because all of the applications were already in the previous paper. Anyway, so, and then there are some remaining good test cases. And the first example that I put is to contain a triangle vector, where a triangle vector means a bunch of disjoint triangles that looks like this. So in this case, we know that it was proved by Johansson, Kahn, and Wu that the actual threshold is this times this, where this is the expectation threshold. And then we have this strange log and fractional log n gap. And we are trying to understand this gap, and we are trying to prove this bound using our approach in the Kancke-Lai conjecture, but so far we don't know how to do this. And another example is another random graph model that is called K-out model. And roughly speaking, in this model, we consider a different random model so that there's no isolated vertices in the first place. So that means for each vertex, each vertex chooses some number of like mates or some member of neighbors. So this way, there are no isolated vertices. And if we consider this random graph model, then we know that, for example, if we consider a perfect matching, then we have this bound which corresponds to P equals 1 over N, which means there's no, I mean, maybe I should say, so in this values corresponds to there's no gap. So it looks like if we force that there's no isolated vertices, then there's no log n gap. But so we are trying to prove this result using our approach in the Kancke-Lai conjecture, and that's one of the things that we are doing now. Okay, so yeah, and then thank you very much for your attention, and I'm gonna continue with the proof after this talk.
Thank you very much. Any questions? Maybe for the recording, use this.
I'm loud enough, I think. Yeah.
Mics.
Actually, the thought I had relating to making the cover approximate is not related to fractional covers, but it's more like the idea of allowing some objects not be covered somehow. Mm-hmm. Because you might, you're using the sum of Q to the size of S lower bound in order to establish that less than half in order to establish that Q is a lower bound for PCF. But even if you sort of miss covering some object, there might still be some sort of auxiliary argument that tells you that you don't miss out, right? So is there some idea like that?
So yeah, so our proof for the Kancke-Lai conjecture uses that argument, uses the idea of like, so we call that a partial cover. So we don't cover the entire thing when we use it. Yeah. Okay.
So that's going to show up in the proof?
When we discuss the proof? A hint on that, yeah.
I have a mic. Can I ask a question? So you said earlier the Fourier analysis didn't succeed in proving what you proved.
As far as I know, yes. So in the Kancke-Lai conjecture, I mean, in the paper that Kahn and Kallai posted their conjecture, as far as I know, they also posed some like possible approaches using Fourier analysis.
I see.
But yeah, I heard that people tried, but they didn't.
Right. But does your approach might say anything about the sharpness of the thresholds, the type of threshold?
No. Yeah,
definitely so, or it's a matter of just sharpening the technique, or for sure the approach you proposed is not going to have any bearing on the sharpness of threshold.
So as far as I know, our technique doesn't have to do with sharpness of the threshold. Yeah.
No questions?
Purely informational question. So this has to do with the beginning of your talk. You made some comments about satisfiability and so on, right? You talked about satisfiability in the beginning of the talk, but there people talk about literals. So you have both the X and the complement. So how does that work with the notion of monotonicity?
So what I know is, so in that satisfiability conjecture, they actually care about the constant vectors.
So you talked about not satisfiable as somehow being a monotone property.
Yeah. At the close, it's not satisfiable. At the close, it's still not satisfiable.
I thought it was like the values of the variables are changed to one.
No.
All right, okay.
I mean, there'll be more opportunities for questions. So if you want to do the proof now, whoever wants to stay, one thing the chat, no questions.
Also, can I just continue? There's no break.
You can take a break if you want.
In front of this audience.
Right, you want to go out, grab the break. But I think we'll just continue.
Oh, this is the first training.
Do you want some cookies? I can go back.
Thank you very much. Oh, but I'm hungry. Okay, so we are here. This is the. Let me have some water. Okay, so we want to prove this upper bound on the Kancke-Lake conjecture, and let me just reformulate. So let me introduce our reformulation. And what we actually proved is this reformulation. So in this reformulation, we introduce another hypergraph H, and this H is just a collection of all of the minimum elements of F. So for example, if F is to contain a perfect matching, then H is the collection of all of the perfect matchings. So this is just like if F is here, then we collect all of the minimum elements, and this is H. Then our reformulation is this. So we showed that there exists a constant L, which is different from K, such that for every L bounded H, where this L bounded means for every S in H, the size of S is at most L. So this just corresponds to the fact that the definition of L of F, right? So this little L is just equal to this little L. Okay, and we showed that if P is above the expectation threshold of this bracket H, because H is the collection of all of the minimum elements, so this bracket H is just F. We just change our viewpoint from an increasing property to a hypergraph. So we showed that if P is larger than the expectation threshold of F, which is this bracket H, then with M this quantity, and when you look at this, so this is just changing from a binomial random variable to the random variable with fixed size. So if we let M to be the expected size of XP, so this is basically the expected size of XP times log of L. Right? So if we fix M to be the expected size of XP times log L, then this XM, so this is a random subset of X of size M. So we just fix the size, and then we choose a set of the given size. And this XM contains a member of H. This contains a member of H means XM lands in F. So XM is here. This is the meaning of XM contains some member of H. And we showed that this probability tends to 1 as L tends to the infinity. And I want to see if this reformulation makes sense. So again, we are talking about the upper bound on the threshold, which means if we are above this value, then we want to say that our random variable XP lands in F with high probability. And then we just reformulated this property by our XP contains a member of H with high probability.
Oh, but you have to constant.
Also here, but as soon as we have this with high probability statement, then we can handle this small L case by adjusting the constant.
No, but you have your big L is now what used to be the K.
Oh yeah, sure. But there is some
big L is K for the, constant number.
Yeah.
Versus P.
Could you say that?
It's just the analog of K.
Yes, it's an analog of K. Yeah, but they are not. Yeah, yes. But because they are not exactly equal, so I just use the different constants. But yeah, they are the same thing. Okay, again, what we did is reformulate the Kancke-Lake conjecture to this containment statement, and this is okay for my audience. So in the upper bound, it's just we show this containment happens with high probability. Yes.
Should I think it is a constant, or is it?
No, this is a variable. So we show that. So this little of L means this is little of 1 as L tends to the infinity. So L is a variable. So for example, we can think about like L is the size of a perfect matching or something. Yeah. Yes.
X sub m is XP restricted to the realization where the size XP is.
Also, Xm just means we consider all of the subsets of X of size M, and then we choose one of them. Yes. And then now we are working with this containment statement. That's what we do. So yeah, okay, so this is our statement, and I just visualized our situation. So this big rectangle, this is our universe X. And then now we have H, and then those circles are the elements of H. Okay, so for example, if our increasing property is to contain a perfect matching, then those circles are all of the perfect matchings in our H set. And in this case, we want to show that Xm, so if we sprinkle our random elements of size M, then at the end, with high probability, our random set Xm contains at least one member of H with high probability. And if you have some maturity in this area or some knowledge in this area, then I think this start is pretty natural. So we choose our random set X, which is another name for Xm, just little by little. So we do not choose our random set at once, but just little by little. So in the first stage, we sprinkle some random elements. And in the second stage, we sprinkle some other random elements, and we repeat this. And at the end of the day, we want our random subset X, random subset W contains a member S in H with high probability. And so in this process, we use randomized algorithm, which does, we iteratively produce a partial cover of, whose name is U of W. So this depends on the choice of W. And because W is a random set, so this is a randomized algorithm because the entire output depends on our choice of W. And here partial cover means, as I said, we do not cover all of the elements in H, but we just cover some part of the elements, some of the elements of H. That is the notion of a partial cover. And here the main point of our randomized algorithm is typically U of W is P-chip, where P-chip is in the second item of the definition of the expectation threshold, if you still remember that. So P-chip means if we add up all of the S in this cover, and if we take P to the S, then this is small. So in my definition, it was 1/2, but actually it can be anything. And in our proof, this small is actually very small. It's exponentially small. Anyway, so I really don't have time to introduce what this randomized algorithm is, but if you want at the end, maybe I can give you a little bit hint of this algorithm. But so really the main point is to show that in this iterated algorithm, so we each time we construct a partial cover, but typically this partial cover is P-chip. That was the goal of our algorithm. And that was the clever point that we borrowed this algorithm, the idea of this algorithm from the sunflower work and the fractional Kankala'i, but our implementation was different. Yes.
So best consensus is the correct factor is related to the empirical statistics of the sizes of the extremal points.
Did you say so?
So I mean, you're looking for some correct factor that is within a range of log of the largest size of a minimal element, right? Mm-hmm. But the picture you're painting suggests that you should be looking at the empirical statistics of the sizes of the minimal elements somehow. Because some of them are big and some of them are small. So some of
we choose the minimum.
Yeah, but some of the true bound may be related to the distribution of the sizes of the minimal elements. Is that true or not?
Oh, so I don't know. So if we iterate this algorithm, then somehow it's very hard to analyze the distribution of what's.
No, of course, yeah. I'm just asking about your guess. That's all.
So
just the big picture. That's all.
I don't know, but because we know that that upper bound is always true in some cases. For example, if we consider perfect matching, then that upper bound is just the truth.
Yeah, but in a perfect matching, all the guys have got the same size, right? I mean, so but for more, that is all the extremal elements somehow have the same size in the perfect matching. But for a more general monotone property, you might have a wide variation in the sizes of the of the extremal elements, and that might determine what that gap is, so to speak.
So yeah, actually we use something like some idea like that to prove the square of the Hamilton cycle. So there was no gap, and the way that we achieved that is we like somehow used that a thing with this large like leftover is very unlikely, very rare.
No, or to say, if you look at the monotone property that you're looking at, right, there are some minimal elements, but they might in general have a wide variation in their sizes. So I think the picture you're painting suggests that it's the distribution of the sizes that might control what the actual threshold is.
So that means it's not just about the graph property, but like we have this biased distribution at the beginning.
I mean, not just the largest size of the minimal elements, but how much, what the empirical statistics of the minimal elements size is. That's just a guess. I was just wondering if you think from it.
Yeah, I think that makes sense.
Okay.
Yeah. Okay. Okay. Anyway, so yeah. But somehow when I was working on this problem, we had some typical examples, and those were graph containment. So somehow we have this uniform situation. But I think, but I understood your suggestion. Okay, anyway, so we are in the middle of this randomized algorithm. And as I said, the main point of our algorithm is to show that typically our partial cover is p-chip, which means this expectation value is very small. And then when our algorithm terminates, then this is a randomized algorithm. So we do not have any specific result, but it allows two possible outputs. The first output is either U covers H, which means, so even if we have constructed a partial cover, but one possible output is this partial cover is actually the entire cover. It covers everything. And the second possible output is our goal. So the second output is something desirable, and the first output is something not desirable. And then what we showed is the first output is very unlikely, which gives us the conclusion that the second output is much more likely. It's very likely. It happens with high probability. And then the way that we showed that one is unlikely is just the definition of the expectation threshold. So this is the situation. So this rectangle is the sample space, which refers to the choice of W, choice of our random set W. And our main point says that for most of the choices of W, U is cheap. The partial cover U is cheap, and it's very unlikely that U is expensive. And then now we apply our assumption. So we assumed that P is larger than the expectation threshold. Well, what does this mean? This means the expectation threshold is the largest value that admits a cheap cover, that admits this expectation small, that admits a cover whose expectation is small. So that means if P is above this expectation threshold, then we cannot have a cheap cover. So that means if our U happens to cover H, then this event must be inside this small area. This is where one belongs to. Because once again, if one happens, then if U covers H, then you cannot be cheap by the definition of the expectation threshold. So one is here, so that means one is unlikely. So that concludes that we have two with high probability. So this ends the proof. So really the main part is how to design this randomized algorithm and then show that our partial cover is usually cheap. And so, yeah, but I don't know how much I can explain about this randomized algorithm. And so let me close for now. But if you're interested, then I can say a little bit more about how to design our randomized algorithm. Yeah. Let me stop here and then.
Yeah, question.
So you had X finite, but with this theorem, are you able, through some limit argument, for example, to give a solution or a better bound to a problem whose statement does not live in the finite world?
I'm not sure about that question. If n, okay, yeah, if n is infinite, but n is infinite, if our ground set is infinite.
No, I mean like if there is like, if say you wanted to solve something of the square grid and you were approximating the square grid like Z2 by larger and larger, you know, finite grids, like, is there a statement which lives on the infinite one that you could use this for?
Like some external combinatorics can be formed in terms of graph ones.
So,
so could you assess some version of the Anka-like conjecture for graph ones?
Rather like a particular application. I don't think there at this point would be a generalization like a theorem. You know, could you?
Right. So she's asking generally, is there some notion of pushing this up to some infinite combinatorics?
I haven't considered that, so I don't know for sure for now. But
yeah. So what is the definition of U? Is U done?
So U is just a name for a partial cover. So it's just, yeah, U is a name for a partial cover. We haven't defined it. It needs a definition, but I haven't introduced it.
So what is the case one that U covers H?
So in our algorithm, we always produce a partial cover whose name is U. And number one says that in the first possible output is U is not just a partial cover, but the entire cover.
Why is it bad?
Oh, no, it just says that there are two possible outputs and the desirable output is number two.
Yeah, so it's bad. If one happens, you don't get two. So in that sense, it's bad because you want to.
No, it's not like if one happens, then we don't have two. It's just saying that, so in order to say that two happens with high probability, we have to say that one does not, one is very unlikely.
No, I mean, I thought, well, also implies that it covers something.
Yeah, you cover something, but that, in that case, U is expensive. You construct a cheap cover.
I think maybe the thing is like U doesn't have to be like U is not the same as W. W is what we want to contain a member of H.
Yeah, and also this notion of cover, this goes back to Christian's question. Is cover actually means you're inside some hyper-edge, right? Whereas you actually want to contain some hyper-edge. So yeah, covering is kind of bad. Right? You want to contain.
But, I mean, the expensive ones are bad. Cheap ones are good. Those are just two possible outputs. So at this point, there is no ethics. But what we want is number two. And one way to show that two happens with high probability is to show that one is unlikely.
So, so you said that U is randomized. So that's
yes, I mean U is the product of the randomized algorithm when where the random variable is known.
Oh, okay.
Yeah.
So it's not like it's a deterministic algorithm as a function of W.
Oh, yes. So whenever we choose W, we have U. So
okay.
U is a product of this algorithm.
Okay.
Yes.
I have another question. So you said this capital L is different from what you ultimately have for the capital K.
Yeah, because we need some modification, but that's not a big deal.
Is it because you move from xn to xp?
Oh yeah, then also because here L goes to the infinity, so we need some constant adjustment to handle small L.
Oh, okay.
So our Kaplan conjecture holds for every L.
Yeah.
So in that statement, L does not have to be large. But in this statement, L is large.
Small statement.
Small L. There are two L's, right? Yeah. I'm sorry.
So, but my question is, why is this capital L different from the capital K you get?
Because so here, this statement is for small L large. So this statement only covers large, small L.
So if this small L is large enough, then is this capital L equal to capital K?
Okay, no. L times log little L.
No, I mean, yeah.
I think the answer is yes. But, maybe there are other reasons, but one of the reasons is the little L is may not be big enough.
You call it
Does it have anything to do with the standard sprinkling outcomes that people construct the giant?
Oh, okay. I need information for the standard sprinkler.
I think she's just using randomly. Yeah. Just a little manner that I prefer. It's like something.
So that's expose something or sprinkle random edges.
Yeah. Just kind of exposing.
Yes, exposing random edges. But we also say sprinkle. Oh yeah, uniform and random.
I see. So that is where it's.
You get anything useful at all from the second moment method, which is often the method of choice to show the final matching.
Meaning for the proof of this argument?
Yeah.
So for this proof, this proof is very easy. So maybe I can say the most advanced technique that we use here is Markov's inequality. So if we didn't even get to the second moment.
But it was still small, but it's innovative. But vanilla approach would be the second moment, which obviously fails, right? But I'm just curious. It fails or it's complicated. What happens if you try to use the second moment argument to prove the Kampf-Light conjecture?
Okay, so I haven't tried it, but I know some attempts to prove something using the second moment method, but it didn't work just because the variance was too large.
Because
the variance was too large. Yes, the second moment was too large.
So I'll ask a quick question. So you explain why P comes in this argument, right? Yeah, I mean, so you explained why M has to be proportional to little p.
Oh yeah, because we consider this fixed size.
Yeah. So what? So where does log L come in this argument?
Oh, so here the size of each WI is exactly corresponds to P, and then we iterate this process by log L times.
Still, because you want to contain a set of size L, so at each time you kind of double.
Yes. Yes. Yeah. So it's like, so when we consider this private measure or whatever any spanning graph, we know that if it's like, so for example, if to contain for example, let's consider a path, then we know that to contain a path of size like 0.9 times x, then we don't need this log L factor. But if each time we collect like 90% of the entire universe, we know that we repeat this by log L times. So that log L exactly comes from that argument.
One minute to 5 o'clock. So if you want to squeeze in one more question. Okay, where are these why are these two the only possible outcomes?
Oh, by the design of the
also,
so this randomized algorithm is really nothing trivial. It requires some clever idea, which is motivated by sunflower. Okay.
People want to stay another half an hour, see what U of W is. Any final thoughts or questions?
So now we go on.
All right. So thank you very much for